Ethine, commonly referred to as acetylene, is an important feedstock for the synthesis of a variety of organic chemicals and polymers. It is mainly produced from the steam cracking of hydrocarbons or partial combustion of natural gas. In such processes, CO2 is a co-product and needs to be removed to produce C2H2 that is desired by industry. Industry demands C2H2 purities in excess of 99%. And in this presentation, we examine pressure swing adsorption technology for C2H2 CO2 separations and how to evaluate MOFs for use in such PSA units. The separation of mixtures of ethine, C2H2, also called acetylene, and carbon dioxide is important industrially for production of pure ethine. Typically, the purity requirement is 99% plus. A PSA scheme for using an adsorbent that selectively adsorbs C2H2 is shown here. It consists of pressurization, an adsorption cycle in which rich CO2 is removed at the top, followed by co-current blowdown, and final countercurrent vacuum blowdown to recover the desired high purity product. Any CO2 that is remaining in the void volume and inside the pores will contribute to lower purity of the product. In order to achieve high product purity at high recoveries, it is important to choose an adsorbent material that practically rejects CO2 entirely into the gas phase and does not adsorb CO2 at all. Let us examine the separations performance of 9 different MOFs, all of which are selective to ethine. These graphs show the IAST calculations for mixture adsorption equilibrium. The left graph here plots the CO2 uptake against the ethine uptake at a total pressure of 100 kilopascal and temperature of 298 Kelvin and an equimolar ethine CO2 mixture. It's interesting to note that FJU90 has a CO2 uptake about 2 orders of magnitude higher than these 3 MOFs shown here, ZNU1, CPL1, NH2, and copper impregnated in UiO66. We return in a later slide to the significance of the small uptake of these MOFs for CO2. On the other hand, FJU90 has also a significantly higher uptake of ethine than the other MOFs. Indeed, the ethine uptake of FJU90 is twice that of ZnU1. The right-hand side graph plots the separation potential against the adsorption selectivity. The separation potential is represents the maximum amount of C2H2 that can be recovered in the desorption cycle. Based on this metric, FJU90 is the leader of the pack, and based on selectivity, CPL1NH2 is topping the list of MOFs on the hierarchy of the adsorption selectivity. So the message to emerge from the IAST is not all too obvious, because FJU90 has the highest separation potential, but the desired product is only available in the blowdown phase. So we really need to simulate not only the adsorption cycle, but the desorption cycle, in order to be able to properly evaluate the performance of these 9 MOFs. Let us first examine the separations with 2 different MOFs, FJU90 and ZnU1, and let's first consider the adsorption cycle in the PSA scheme. For ZnU1 and FJU90, the transient breakthroughs are shown in this graph, where the dimensionless concentration at the adsorber exit are plotted against the parameter Q0T divided by the mass of adsorbent. The black lines represent the simulations for ZnU1, and the blue lines are the simulations for ZJU90. The blowdown operations will start just before C2H2 starts breaking through into the column exit, and these are indicated by the black and blue arrows respectively. Since C2H2 is the desired product, it is of importance to have an appreciation of what remains within the adsorbed phase up till the point at which the blowdown operations start. For this purpose, we shall examine the animations for the average loadings in the adsorber as a function of the adsorber length. The y-axis plots the component loadings for ZnU1 as a function of the adsorber length, and this animation, to be shown, plots the component loadings in the adsorbed phase as a function of the adsorber length for FJU90. Let's start with the development of the molar loadings in moles per kilogram for ZNU1. Red is C2H2 and blue is CO2. The corresponding development of the component loadings in FJU90 are shown in the animation below. Red is C2H2, blue is CO2. It is noteworthy that with FJU90, the adsorbed phase loading is in excess of 5 moles per kilogram for FJU90, but for ZNU1, the adsorbed phase loading is 2.8, significantly lower. On the other hand, the CO2 loading here is practically nothing, is about 0.2 or so. Whereas for FJU90, the CO2 loading is about 1.2. At this point, the adsorption cycle is terminated and the blowdown operations will need to start in order to recover the adsorbed C2H2 that is shown here in red. We still have to wait for the for this point to occur when the blowdown operations will start for the black MOF, which is ZNU1. At this time, the adsorption cycle is terminated and the blowdown will start. The important differences in these two MOFs is clear. FJU90 has a significantly higher CO2 in the adsorbed phase of the order of 1.2 moles per kilogram. It also has a higher amount of C2H2. But when blowdown occurs, both components will be desorbed and will exit the column simultaneously. We employ countercurrent blowdown, which means that the products are removed from this end. So the amount of CO2 is a significant proportion as compared to the amount of C2H2. For ZNU1, the situation is quite different. The CO2 loading at the start of the countercurrent vacuum blowdown is of the order of say 0.03 moles per kilogram, significantly smaller than the value for FJU90. So when both components are desorbed, the composition of the desorbed gas phase will be in this proportion for ZnU1. Following the simulations of the adsorption cycle, we performed simulations of countercurrent vacuum blowdown for the selective MOFs. The obtained data on product recoveries of C2H2 and CO2 and the purity of the desired product are plotted in this graph. We choose the parameter Q desorption times the time divided by mass of adsorbent as the x-axis in all three cases. Q desorption is the volumetric flow rate of gas exiting the bed, and this is dictated by the draw-off rate used for the vacuum pump. We employ deep vacuum to desorb the products. Let's first have a look at the recovery of the desired C2H2. The cumulative value of C2H2 recovered from the blowdown is expressed as moles of product recovered per kilogram of mass of adsorbent in the bed. The highest product recovery is realized with FJU90. But the problem is that FJU90 also recovers a concomitantly large amount of CO2. The amount of CO2 recovered is the lowest with these two MOFs that practically reject CO2 into the gas phase. But these two MOFs do not have productivities of C2H2 that are comparable with that of FJU90. The purity of the desired product, C2H2, is plotted against the effective time, and we note the highest purities of about 97% are realized by the MOFs that practically reject CO2 into the gas phase. Whereas the product recovery with the FJU90, for example, is only 80%, far lower than the desired high purity requirements of industry. A good compromise would be to use ZnU1 that has a high purity of C2H2 along with a reasonably high product recovery of C2H2. In this graph, we plot the C2H2 recovery from blowdown operations against the separation potential determined from the IAST calculations. For all the MOFs, there is a roughly linear relationship between the product recovery from vacuum blowdown and the separation potential, indicating that these IAST calculations provide a reasonably good measure of product recoveries. Let's examine the product purities that are realized after vacuum blowdown. These are the values from the vacuum blowdown simulations shown in the previous slide. They vary from 75% purity for C2H2 nickel I to about 97% for these three MOFs. The product purities are plotted against the IAST calculations of Q1, which is the component uptake of ethine divided by the total uptake and multiplied by 100. So you can see that there is a practically linear relationship between the IAST calculations of the product purity that is expected in vacuum blowdown with the actual purities that are realized in the blowdown simulations. To stress the point that was also made in the earlier slide, FJU90 has the highest C2H2 recovery, but the product purity is only 80%. Of these three MOFs, ZNU1 has the highest value of the C2H2 recovery, and therefore it is likely that ZNU1 is the optimal MOF for this separation. A different approach would be to select a MOF that is selective to CO2 such that C2H2 can be recovered in the adsorption cycle. This is what we are going to examine in the next slide. Professor Zhao at the National University of Singapore and his group have reported results for cerium-4 Mil144F MOF that is CO2 selective, and this MOF is of potential use for producing high purity C2H2 from a CO2 C2H2 mixture. We present simulations of transient breakthroughs in a fixed bed packed with the cerium MOF. Two types of simulations are compared, one in which diffusional resistances are duly accounted for, and the other type of simulation in which the diffusional effects are ignored, and we assume that the diffusivity is divided by the square of the radius of the crystallite is very large, leading to practical equilibrium between a gas mixture and the particle of adsorbent at any position in the fixed bed. Let's have a look at the two simulations. I will run these simultaneously. I would like you to note that the simulations with diffusion have a more distended characteristic than the simulations that ignore diffusion. If diffusion effects are ignored, you get very sharp fronts. This is the front of C2H2 as it traverses the fixed bed and exits the column, and CO2 that is more strongly adsorbed is leaving the column at a much later stage, leading to good separation. This graph shows a comparison of the experimental breakthroughs for C2H2 and CO2 shown in red and green, with the two types of simulations that were described in the previous slide. The simulations indicated in black are the ones that include diffusional limitations, and the simulations that are indicated in blue are the ones where diffusional influences are ignored. We see sharper breakthroughs with the equilibrium based simulations shown in blue. Sharper breakthroughs result in higher productivities. So diffusional influences have a tendency to lead to distended breakthroughs and lower productivities. The message we draw from this comparison is that for a realistic prediction of productivities of desired products in transient breakthroughs and fixed bed adsorbers, we need to consider intracrystalline diffusion limitations.